Okay, welcome back. So now in this video, we're going to be talking about damped systems. This is a systems that basically they have damped. So you can see this is a mass spring damper system. You can see now the middle term appears. And the only difference is that this time we are adding this dashpot. And what this dashpot does is basically that it dampens the system. It basically adds a little friction so that instead of the system oscillating back and forth indefinitely, when you add this dashpot, this basically takes away energy in the system and basically will make that our system basically goes to a stop eventually. But depending on the constant C, depending on whatever we get, we can have this we can have our system stop almost immediately to taking a while and so on. So you can see we have our equation of motion here. We get this one, same thing from our free body diagram. You can see still a second order ODE. And whenever we solve it to the characteristic equation, we're going to get something like this. And we also have two roots. And depending on what those roots are, we can have three different cases of damping. So, and well, basically depending on whatever that constancy, we're gonna get those three different cases. And you can see these roots are imaginary, well, most likely imaginary, but you know, they can also be real or the same. So basically you can see these cases are pretty similar to the cases we have been working on a mathematical sense. So we have case one, where that's C squared. It's greater than 4 times mk, which is, you know, the inside of a quadratic, what's it called, like a quadratic, the square roots. So if we get that, that's the case, we're gonna get distinct root of roots. So, you know, it's like case one, right? Like we've been talking about before. But in the applying it to the systems of modeling mass spring damper systems, when you get these kind of roots, you're gonna get overdamping. And that's represented by the red line over here. And basically what happens is that the system does not oscillate. It basically just moves down and then just slowly goes to zero. You don't really get a oscillation. So there's too much damping, there's too much friction that you don't oscillate. You just slowly go to zero. Then you have case two, where you have two double real roots, and this is what we call critical damping. So here the system, it's almost like that part where it wants to oscillate, but it doesn't. So it's kind of in between the middle. So we get something kind of looking kind of linear here, but then it just goes to zero real quick. It's enough damping that it just happens super fast. And then you have your case three, of course, the complex conjugate roots, where you're gonna have the exponential times the sinusoidals. And in this case, because we have the middle part, and since the middle part, it's not a zero, like in the mass spring system, we're gonna have the exponential times the sinusoidals. In this case is when we have, this is where we're gonna be having the underdamping. And you can see that the underdamping, you can see our system basically oscillates, but those oscillations become smaller and smaller until eventually reach zero. So there's usually an overshoot, and then they oscillate about the 0 point. And that oscillation is basically caused by the sinusoidal, so it's cosine sine. And that exponential decrease is, of course, due to our exponential term here. So it's basically how they look like. So in whatever application you're working with, you need to determine what kind of damping you want to have. All of these constants, the M, K, and the C, all of these are properties of your materials. The stiffness, the damping constant, the mass, these are properties of your material. So whatever material you're working with, let's say you're modeling the suspension for a car, you use this type of model to simplify your design. You have the mass, which can be the wheel, and then you have springs and dampers, the suspension. Basically, anything that has mass, you can model it as this kind of system. If you take the vibrations class, this is basically what they do. It's basically the way that we solve our problems. We'll try to upload maybe some other videos regarding that class later on, but this is as far as we're gonna get at this moment for this topic. But it is a really interesting series that you should really look into if you're interested in designing suspensions or many other things. So let's do an application problem and let's see how changing the damping affects the whole system. Okay, so in this example, they're asking us, how does the motion in the previous example or in the previous video that we did with the mass spring system, how does the motion change if we add a damping constant? And we have three different values. We have the damping constant of 100 kilograms per second, 60 kilograms per second, and then 10 kilograms per second. So basically, we're gonna solve this problem 3 different times with 2 different constants. And just to basically, I guess, help you guys remember what were those values that we have from the previous video. If you haven't seen it, go watch it right now. We know that the mass was 10 kilograms. We know that the stiffness was 90 newtons per meter, and we knew that omega was 3 radians per second. So with these results, basically we need to apply, this will be for the case 1, where C it's 100 kilograms. So doing that, we are gonna have then the following. So we'll have here that y double prime plus C over m y prime plus k over my is equal to 0. So just substituting the numbers, we get y double prime plus, that's 100 over 10. That will be 10 y prime plus k over m. We know that that was the square root of, or you can have 90 over 10. That's still 9, right? So that's 9y equals to 0. We don't apply the initial conditions yet. We know how to solve this equation. So it's pretty straightforward. We do characteristic equation, and we're gonna have lambda squared plus 10 lambda plus 9 equals to 0. So solving this one, we can factor this one out, right? So this will be lambda plus 1, lambda plus 9. And therefore, we're going to get that lambda 1 is equals to -1, and lambda 2 equals to -9. And because these are 2 real roots, we know that this is a case 1. And because it is a case 1, our solution will be in the form of, let's see here, our solution will be y of t is equal to C1 e to the -t plus C2 e to the -9t. And this is basically our general solution for this system. This is my general solution. And now we need to apply those initial conditions to determine what the actual equation is. So let's apply once again those initial conditions. So we had that y of 0 is equals to 0.16. So from this one, we're going to get 0.16. It's equal to C1 e to the 0 plus C2 e to the 0. And then since e to the 0 equals to 1, we have 0.16 equals to C1 plus C2. Now we need to find the other equation, the y prime of t. So we didn't do that. So y prime of t, that's equal to negative C1 e to the -t minus 9 e to the -9, or 9 C2 e to the -9t. And whenever we apply the initial conditions now, So y prime of 0 equals to 0. We're going to have here then 0 equals to negative c1 e to the 0 minus 9c2 e to the 0. So from here, we're going to have that c1 is equal to negative 9c2. And from solving these two equations, you can use any method to solve them. We're going to get from here that C1 is equal to 0.18 and C2 is equal to negative 0.02. So then my solution for this one, my particular solution, I'm right here, it's y of t equals to 0.18 e to the negative t minus 0.02 e to the negative 9t. And this is our particular solution for that specific problem. So this is how it looks like when we have the overdamping. So basically this case, I'm gonna write here, we have overdamping. Okay, so let's continue now with the 60 kilograms per second. So let's do case 2. I'll do it in blue. So let's see here. So this is for number 2. So we have y double prime plus 60 over 10 y prime plus 9y equals to 0. So then from here, we're going to get y double prime plus 6y prime plus 9y equals to 0. So we know how to solve this one. Characteristic equation, lambda squared plus 6 lambda plus 9 equal to 0. So solving this, we're going to get that this can be factored out into lambda plus 3 times lambda plus 3 equals to 0. And because of this, we know that lambda 1 and 2, both of them are going to equal to negative 3. So both roots are the same. So this is therefore a case number 2. So two real roots that are the same. So when that happens, then my solution will be here, y of t, it's equal to c1 e to the negative 3t. Let me make it a little bigger. This is negative 3t plus c2t e to the negative 3t, right? Because this is different real roots. So this is my general solution for this one. And now, once again, I need to apply the initial conditions. I need to figure out what that other solution is. So let me write it here. Let's continue working here. So y prime of t will then be equal to negative 3c1 e to the negative 3t minus 3c2 e to the negative 3t plus c2 e to the negative 3t, right? Because this one has this two terms here. So we need basically apply product rule. So let's apply initial conditions and let's see what do we get. So applying initial conditions here, we get that 0.16 it's equal to c1 e to the 0 plus c2 times 0 e to the 0. So from here, it's pretty straightforward that this one will cancel and we'll get then c1 to be equal to 0.16. And using the second initial conditions, we have 0 equals to negative 3 C1 e to the 0 minus 3 C2 e to the 0 plus C2 e to the 0. And after solving and simplifying everything here, we already know the value for C1. You guys can simplify and solve. You can see it will be negative 2 and so on. We're going to get that C2, it's equal to 0.48. So for this specific problem, the final solution, I'm going to write in here, y of t, it's equal to 0.16 plus 0.48 t e to the negative 3t. And this is a particular solution for this problem. So now we have the last one, and we know that this one, because it was a case 2, this will be a critically damped. And so we have one more, and I think you can already expect what we're gonna get, but let's still apply it. We have the case 3, where basically the damping is 10. So we'll have y double prime plus 10 over 10, that's just 1, plus 9y equals 0. We know how to solve this, so we get lambda squared plus lambda plus 9 equals to 0. And basically from here, we cannot factor out. We need to apply the quadratic equation. And because of time, I'm not going to do that here. But you can see that after we solve it, lambda 1 and 2, we're going to get negative 0.5 plus minus 2.96 I. And because of this, this will be a case 3. You can see that this time we don't get pure imaginary, we get complex numbers. And this is a case 3. And therefore, my solution here, I'm gonna write here, my solution, my general solution will be e to the real part, negative 0.5t times a cosine of 2.96 t plus b sine of 2.96 t. So one thing you will notice here is that this 2.96, it's close to our natural frequency, but it's not exactly natural frequency. So you can see that this case in the modeling, whenever we don't have the damping, it will oscillate natural frequency, but because we increase it, we have damping here. In this case, it's the underdamped. You can see the frequency will be slightly less than the system's natural frequency. And that's where we get the underdamping. So after we apply the whole everything, I'm not gonna do the whole process again. But after we apply the initial conditions, you guys can do that on your own, or you already saw the example. After I apply the initial conditions, I will get this to be y of t is equal to e to the negative 0.5t times 0.16 cosine of 2.96t plus b, well, not b, this is a 0.0027 sine of 2.96t. And this is what we would call our particular solution for this problem. And that's how basically you solve this kind of problems. You can see it's pretty straightforward, this application. If you're interested in learning more about this, we have the whole class for vibration that you should definitely take. But this is something that you can already start applying whenever you want to model any kind of system that has a mass, some sort of damping, and something elastic like a spring. You don't really have to have actual springs and dashpots and masses, but you can model all systems and reduce them to this. So here I'm showing you the graph about how each one of them look. And you can also see the difference between the three. Once again, we have the overdamping, the critically damped, and this last one is the underdamped. And this is the difference. So that's it for today. I will leave you here. And as always, good luck.